that was a pretty cool example, I thought. Here's a good one. Okay, so let's look at this model right here. So we've got this one going here. Okay, so what we're going to do is let's look at how about x prime equals 16 minus 4x minus 2y, and then y prime equal 10 minus x minus 2y. y. I'm going to be quiet. I want you guys to tell me what is the big situation. Last time we had predator-prey. I want you to tell me, you guys tell me, what is the fundamental big situation that's going on here? What is the relationship between x and y? Did everybody kind of write it all these different ways? So I wrote it this way. This way, at first I grouped the x's and the y's together, and then this like this, and then I kind of cleaned it up. So what does this tell you right here? Without a y, how would x grow? Logistically, with the carrying capacity of the environment being 4,000, whatever it is. Okay. And then here, without the x, how does y grow? Also logistically, with maybe 5,000 or 50,000 or whatever it is, okay? All right, so, but now, if you look at this, so both grow logistic growth. This is logistic growth. Without the other, logistic growth. Right here, this is logistic growth. Without the other guy. Now, when you have interaction, does the interaction harm or benefit x? Harms. Does the interaction harm or benefit y? Both? Okay. So they're both bad for each other. So is this predator-prey? Is it cooperating or competing species? Competing species, right? They're both bad for each other. They're competing. So let's go ahead and see what happens. We have competing species. Oh, by the way, predator prey can be things like, the prey doesn't have to be an animal, it could be like a grasshopper and grass. Okay, so. Okay, right. So, okay, but this is competing species. Okay, so let's just go ahead and do that. All right. So what's the first step? Stationary. So does everybody see we did stationary points or stationary solutions, right? Then we did semi-stationary, and when we're doing this, does everybody see these straight lines right here? These were the semi-stationary, and then these are the non-stationary. So we went stationary, semi-stationary, and then we did non-stationary. Okay, so that's what we're doing. So semi-stationary is set the derivative, right? I'll just go x prime equal. So I use this one. This is the best one for the stationary, right? So you go 16 minus 4x minus 2y, x equals 0. Y prime equal 10 minus x minus 2y, y equals 0. Okay, it doesn't matter which one you choose, so I'm just going to do the bottom. Now, follow the logical thread carefully. This one or this. And you can only do this for 0. One is 0, the other is 0, okay? Then what you do is you always bring down the other guy. So let's do it, the easy one. So we're going to bring him down. So that's 16 minus 4x minus 2y, x equals 0. Because I used to have to grade all these Lagrange multiplier things. Do you remember that? You use something that's kind of similar when you're solving, and it's just so much work. So, and everybody doesn't follow the logical thread, so they just start mixing and matching. So put the 0 in here, you get 16 minus 4x, x equals 0. Okay? Now, break this up. 16 minus 4x equals 0, or x equals 0. Okay, so then obviously x equals 4, x equals 0, but it was under y equals 0. So what you have is 4 comma 0, 0 comma 0. Okay? Then on the other side, again, you bring him down and stick him here. So 16 minus 4x, and then x equals 0. Okay, so now you have these two right here. Again, probably the easier thing to do is just to split that into two pieces. So now you have x equals 0, or 16 minus 4x minus 2y equals 0. Okay. Now, again, we're here under this guy. Okay, so I'm going to do the easier one. So always go for the easier one. Okay, now, so I'm going to bring him, so this is 10. So if the x is 0, 10 minus 2y equals 0. Y equals 5. Okay? So this is 0, 5. Okay? Now, again, we're under him. So I'm going to just recopy him. And then this one is just yucky. There's nothing you can do. Okay? So what I'm going to do is I'm going to just go ahead and subtract. All right? So I'm going to get rid of the 2y. So I'm going to go subtract from both sides. So 16 minus 10 is 6. 4 minus the negative x is negative 3x. 2y, negative 2y minus negative 2y is 0, equals 0. So the x is equal to 2. Okay? If the x is equal to 2, just take one of them. So put the 2 in, so I say 8 minus 2y equals 0. Y equals 4. Right? If I had plugged the 2 in over here, that would be 8. Yeah, it's still the same thing. So the answer is 2, 4. So does everybody see? Okay, you don't mix them after say 2 and 0, and then 5 and the 4, or I mean like the 2 and the 5, and then the 4, you know, the 4 and the 4. Okay, so you don't mix and match. Okay, so what you do is you just write them down so you can do 0, 0. We had the 4, 0. We had the 0, 5, and then we have 2, 4. Okay. And it's exactly what you would think it is, because you can see that we're going to have, you know, your carrying capacity of the environment. Okay, so these are our stationary solutions. Then what we want to do is, let me go ahead erase this, okay? And put this, let's put everything in. So again, if we're dealing with a population, you know, we don't need to worry about the negative. If I do not give you a story like that, then you do have to deal with everything here and here and here and other quadrants, okay? But for a story like this, obviously you're going to focus in right here. So this is the 0, 0. And then what we have is 1, 2, 3, 4. So 1, 2, 3, 4. Right? And then you have 0, 5. 1, 2, 3, 4, 5. And then you have 2. And then you have 4. Okay, so here are our stationary points. Then, what's the second step after stationary solutions? Semi-stationary solutions. Very good. Semi-stationary. Good. All right. So now, what we're going to do is we say to ourselves, what x, so dx dt equals 16 minus 4x minus 2y, x equals 0. What x makes this 0? And the answer is 0. So if x is 0, now plug him into the other one, dy dt, and what you have is 10 minus 2y, y equals 0. If x is equal to 0, it looks like this, right? So now we'll look at this and tell me, what are the stationary solutions to this one right here? 0 and 5. Y equals 0. Y equals 5. Okay, let's just plug some numbers in. Plug in negative 1. Is that positive or negative? Looks like it's negative, right? Plug in the number 3. Positive or negative? Plug in the number 3. 10 minus 6 times 3. Positive. Plug in the number 6. Negative. Okay? We transfer everything over to this, the x equals 0. Okay? And you guys can see, hey, this is already here. And you can see what's happening. Right. Because that was the carrying capacity for species y. So if there was no x, x equals 0, what happens is you approach the stationary solution right here. You don't get to it, of course. If you have too many beyond the carrying capacity, you approach the carrying capacity of the environment. Okay, so this is what this is. And then, of course, we just go ahead and have this here. Okay, so we'll do the other stationary solution, right? So we'll go ahead and we'll say dy dt equal 10 minus x minus 2y, y. What y makes this 0? What y makes it 0? Yeah. Y equals 0. So then plug it in here, and then you get dx dt equals 16 minus 4x. Plug it into y, so that's 0, and then you have an x. Okay, so well, y equals 0, right? So y equals 0, right? It's a horizontal line. So now over here, what were the stationary solutions for this thing from part 1? We're back to part 1 again of the course. What does that equal? But what will make that 0? 4 and 0. Good. X equals 0. X equals 4. Okay. Plug in negative 1. It looks negative to me. Plug in the number 2. It's positive. Plug in the number 10,000. Or no, just plug in number 5. Negative, okay? We transfer all the information over here, and you can just see what's happening, okay? So here we have, this doesn't mean anything right here. But between 0 and 4, right, species X, if you have a little bit, it will just increase to the carrying capacity of the environment. And then over here, if it's greater than the carrying capacity of the environment, it will decrease. Okay, so that's what it is. Okay, so we transfer the stationary, semi-stationary to this. Okay, so now what we're going to do next is let's go ahead and we're ready to do non-stationary, right? So to do non-stationary, I'm going to go now non-stationary, right? We do non-stationary solutions, so we need to do the Jacobian. Let me write that again. Non-stationary. So we're going to approximate those guys with a Jacobian, right? So one more time. This is the f of x, y. This is the g of xy, right? And remember f is f of xy, g of xy. Okay? So the Jacobian is this guy, and his matrix. This is not the Hessian. Remember the Hessian? The Hessian was when you had partial f to the two derivatives. Okay? That was a different one. Okay. So this is partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. Okay. All right, so let's go ahead. Take the derivative, do you see how this is the easiest one to use now? That was good for interpretation. That was good for finding stationary and semi-stationary. This is good for just non-stationary, doing the Jacobian. Okay, what is the derivative of f with respect to x? And derivative of f with respect to y? Good. Derivative of g with respect to x? Mm-hmm. Derivative of g with respect to y? Good, thank you. Okay, there we go. So now we have the Jacobian, right? And what we're going to do is we're going to linearize around the stationary points. So we have several of them. We have 4 of them, okay? So we're going to linearize, right? We're going to take the linearization of the problem. This is a nonlinear problem. We're going to approximate it by linear. The linear problem is going to be dx tilde dt equal ax tilde. Okay, we'll do it around 0, 0 first. Okay, because that's the easiest. So we plug this in and tell me what is the stationary, what is the matrix? Plug in 0, 0. You get 16, 0, 0, 10. Okay? When it's diagonal, you can just go ahead and you just know right away it's going to be, this is what, let's just say P of z equals z squared minus 26z plus 16 times 10. Okay? So does everybody see this is going to be z minus 16 and z minus 10? So the eigenvalues, or the roots of the characteristic polynomial, are going to be 16 and 10. Okay. When you have 2 positive, what do you have? Nodal source. Do you remember what nodal source was? Was it stable?
It's unstable.
It's unstable. And then it's actually repelling, right? And it's not attracting. Of course, it can't be because it's repelling. Okay, so what we're going to do is we're going to go ahead and find the eigenvectors, right? So here we have this. So we're going to use Cayley-Hamilton theorem. P of A equal the 0 matrix, right? And so I'm going to skip. I'm just going to start to write things down, okay? So I'm just going to go like this instead of writing it every last thing. 16, 0, 0, 10, all right, equal 0, 0, 0, 0. Okay, and so what you have is you subtract 16 on the diagonal, subtract 10, okay? And now you have 0, 0, 0, minus 6. 6, 0, 0, 0. Okay, and remember, eigenvector by definition is not allowed to be 0. Okay, so on this side, what is a eigenvalue? 16. And what is a good corresponding eigenvector? 1, 0. Right, because it's 6, 0. You cannot have the 0, 0, but then you make him, right? There you go. Okay, and then on the other side, what you're doing is you're imagining this turn around. Okay, so then what is the eigenvalue? That value? 10. And what is the eigenvector? 0, 1. Okay. Okay, so what you have is, let me make it blue. So I made this guy blue, right? Okay. So what you have is, you have 0, 1 like this, and they're all going away because it's positive. Okay, so it's like this. And so now, does anybody remember which is the one that you are tangent to? One closer to the 0. So you have 10 right here, and you have 16 here. So you're always going to be tangent to the eigenvector line. Okay. So let's just go ahead and just draw that. So the eigenvector line is like this, right? So that is closer to the origin. So it looks like this. Let me get blue and purple. Okay. So you're going to come in, and it looks like this, right? So that's your nodal source. Now remember, like this. Okay, so why don't we, is there anything else we need to do? Oh, we should write down, you can write down the equation, it's just not too hard, right? You all know how to write the equation for it. Okay, let's go ahead. Let's do another one. So let's do 4, 0. So 4, 0, 4, 0, plug in 4, and 0, what do you get? I think it's minus 16, right? Plug in 4, minus 8, 0, plug in 4, I think I get 6. Is this what you guys got? This seems right, right? So then, does everybody see your eigenvalues are going to be what? Minus 16 and 6, because it's like this. However, let's double check. Okay, so our characteristic polynomial is z squared. This is plus 10z, and then minus 6 times 16. So you can see, yes, z minus 6, z plus 16. Yeah, because your eigenvectors, this is how you factor. Let's do Cayley Hamilton. Okay, so we're going to do minus 16, minus 8, 0, 6, minus 16, minus 8, 0, 6, 0, 0, 0, 0. And then we go minus 6, minus 6, plus 16, plus 16. Okay, And so now what we have is negative 10, 0, minus 8, 0, 0, 0, minus 8, 22. 0, 0, 0, 0. Okay? Okay, so let's write down, okay, so what is a good what is the eigenvalue? 6, and what's the eigenvector? 4, negative 11, right? Then over here, we have another guy, so what is the eigenvalue? Negative 16. It's negative, right? Don't think it's positive. Because this is negative, negative. Okay, and then what is the eigenvector? Not 4, it's 4 over, like this, okay. What about this guy? 1, 0. This guy should be red. Okay. And then the other guy, I'll make him blue. 6, 4, minus 11. Okay. All right, so everybody can see this, and you can see, here we go, the 1, 0. Oh, let's write down the eigenvector line, so you guys have practice with this, okay? So for this guy right here, underneath him, can everybody see that that is y is equal to negative 11 over 4 times x, right? But that's tilde in the tilde system. So actually it should be y minus 0 equal minus 11 over 4 x minus 4, right? Because that's what it's centered around. And then over here, this eigenvector line is y tilde, 0 over 1, so that's 0x, so this is y tilde equals 0. But y tilde is still, subtract 0. So y minus 0 equals 0, so it's y equals 0. So that's the eigenvector line right here. Okay? Okay, so, I should have made that blue. That was supposed to be blue, that was supposed to be red. But okay, so let me just go ahead and draw this other guy. Okay, so you go over 4. 1, 2, 3, 4, down 11. 1, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this slope is sort of like this. Okay? Kind of like that. Okay, here we go. And this one, the eigenvalue is 6, so the arrows point toward or away from the origin? This stationary point. Away, do they point toward or away? Away, because this is the origin in the tilde system. Okay, so it looks like this. Okay, and so you have this, and we know that with 2 of these, right, when they're opposites like this, you have a saddle. Okay, and with a saddle, unstable, not attracting, not repelling. Okay, so now let me go ahead and just draw these guys. So we have this. So what we see is the environment. This is mainly the environmental issue. We have something here that kind of looks like this. So we can see what this is. So it kind of goes like this. And then we have this. Okay. Something like this. Okay. And we have this. Right? Okay. Now what we want to do is we're going to go ahead and look at another stationary solution. Okay, so let's do 5, 0, or 0, 5. So, right, that's 1, 2, 3, 4, 5. Yeah, 0, 5. So let's do 0, 5. Okay, can you guys go ahead? I'm going to be quiet. And you guys do the Jacobian. this in, I think you get -4, right? And this one was 0. This is -5. And then 0. Did you guys get this?
I got 6.
6.
Yeah, I got 6. -4, 6 and 0.
Oh, really? Okay, because, oh, I see, so 6 minus,
What's the?
oh, okay, so was it this?
Yeah.
Okay, so now this is also triangular, so you know that it's gonna automatically be lambda equals 6 and -10, but let's double check. POC, z squared, positive 4z, and then -6 times 10. And you can see z minus 6, z plus 10, yep, it's true. Okay, we'll do Cayley Hamilton. And so 6, -5, 0, minus 10. 6, 0, -5, -10. Okay, and then you're going to subtract -6, add the 10. Okay, and so what we end up having is we end up having 0, 0, -5, -16. 16, -5, 0, 0, 0, 0, 0, 0. And so lambda equal, let's see, this guy is going to be 6, and then the other guy is just simply 16 over -5, right? And then the other guy over here is -10. -10, and then what we have is 0, 1. Okay, 0, 1, you can see it's already this.